All right, good morning, everybody. So today we finish up with alcohol oxidation, and then we'll move on to chapter 12, which is all about resonance and conjugation, and a couple new reactions in chapter 12. So, as I talked about last time, you've got primary, secondary, and tertiary alcohols. And the ability to be oxidized really depends on how many protons there are on the carbon that also has the oxygen. So you'll notice that a primary alcohol has two carbons or two hydrogens on this carbon that's attached to an OH group. So it can be oxidized to an aldehyde. The aldehyde still has one proton, so it can be oxidized further to the carboxylic acid. The secondary alcohol only has one CH bond on the carbon that's bonded to the alcohol, and so it can only be oxidized to the ketone, and there you stop. There's no further oxidation that can occur there, at least not with the reagents that we're talking about here. And then, of course, the tertiary alcohol can't be oxidized at all because there's no CH bonds on that tertiary carbon. So we talked about a reagent, PCC, pyridinium chlorochromate, and this is useful for oxidation reactions. There's only two new reagents to learn here, and they're related, and the mechanisms will be related, and the differences between them are going to become clear if we look at the mechanism. But with pyridinium chlorochromate, you've got a counter ion, that's the pyridinium portion, and then you've got the oxidizing agent, the chlorochromate reagent. And you can tell it's an oxidizing agent because you have an electron-poor metal attached to several very electronegative atoms. And we said that chromium's in its +6 oxidation state. So it's very electron poor. And we will see that in the mechanism, the alcohol oxygen attacks the chromium and the chloro leaving group leaves. You get this Zwitter ionic intermediate. That term Zwitter ionic means neutral but charged, which sounds like, how can you do that? And that's a Zwitter ion is if you have a plus and a minus in the same molecule, so overall it's neutral. Then next, your text shows a proton transfer step. It doesn't actually push arrows for that. It simply says, ooh, proton transfer. But it makes sense that the negatively charged oxygen should pick up the proton from this positively charged oxygen so that the molecule can just be neutral. As I mentioned, I think last time, I don't particularly love this oxygen reaches over and pulls off that proton. Not because it looks so unreasonable, but just because if you ever took Chemistry 552, you would learn that four-membered ring reactions are okay, but they're not super fast. But in any case, you can draw the mechanism this way. The negatively charged oxygen attacks the proton, and then you get the neutral oxygen. And now, attached to the oxygen, we have what is a good leaving group. It's okay if you don't recognize it as such. I wouldn't either, other than that the chemistry works. And so one important feature, though, is to pay attention to the fate of this lone pair that used to be just on oxygen. It forms a new bond with chromium, and those electrons are in that oxygen-chromium bond. Now at this stage, this is the oxidation step. What you've got, if you look at it, is a good leaving group on, we'll call it the alpha oxygen because it bears the leaving group. And then on the adjacent atom, the beta carbon, you have a proton. And anytime you've had a beta proton adjacent to a leaving group, that has set you up for what kind of reaction? Elimination, right? So that's what's going to happen here. An elimination reaction will remove the beta proton and the leaving group is going to leave. Now, what's the base? It turns out the only thing you've got in solution at this point that's negatively charged is probably Cl minus. I don't really like that as a particularly good base. It's also possible that what's going to remove the proton here instead of being Cl minus is actually this negatively charged oxygen from another intermediate. We won't worry about the identity of the base. I'm just going to show the mechanism with some base removing the proton, electrons kicking down to form a new pi bond, and the leaving group leaves. So here is the product of that step. You now have, of course, the beta proton had 2 protons originally. Now it just has 1. This is now an aldehyde, and the aldehyde is oxidized relative to the alcohol starting material. You can tell because the number of CH bonds has decreased and the number of CO bonds has increased. Another byproduct that we can draw here, and we're going to forget about it and not worry about it, but this is the leaving group, and it has been reduced. If you go through and figure out its oxidation state, this is now chromium, and you don't need to know how to do this. This is now chromium 4 instead of chromium 6. Its oxidation state has gone down by 2 because it now has the 2 electrons that were the lone pair on the oxygen. So at some point, some of you have probably been asking yourselves, okay, wait a minute, in Gen Chem oxidation was loss of electrons. So why is it now suddenly loss of CH bonds and increasing in CO bonds? And here you're seeing a reaction that demonstrates both, right? You're seeing a decrease in the number of CH bonds, an increase in the number of CO bonds, and you're literally seeing a pair of electrons that used to be on the oxygen be removed onto the chromium. Okay, questions about that? So that reaction sequence is going to be the same for the other set of oxidizing reagents that we talk about. Now, one question you might ask is, how is this able to stop at the aldehyde? Why doesn't it go on and react to form a carboxylic acid? And I'm going to answer that question, but before I do, I need to show you the method for going all the way to the carboxylic acid, and then the difference between these two methods will become clear. One thing I will say is that PCC, because of the pyridinium counterion, PCC is soluble in organic solvent. And I don't require you to specify solvents in synthesis or anything like that, but a typical solvent for the PCC reaction, excuse me, 1 per lecture, right? Got to get the sneeze out. A typical solvent for this reaction is dichloromethane, or CH2Cl2. Dang, I was just about to sneeze again. That's annoying, right? You got to sneeze and it doesn't come. All right, well, we'll be fine. Anyway, typical solvent is dichloromethane. And importantly, you'll see an important detail here. There's no water present. And you'll see that that's the reason why the aldehyde doesn't go on to become the carboxylic acid. All right, before we get into that in any detail, are there any questions about that mechanism or how PCC works? Yes?
Is the pyridinium counterion, does it separate from PCC?
Yeah, so does the counterion separate from the chlorochromate oxidizing agent? That's a really great question. The answer is I don't know. To the extent can ions dissociate from each other depends on how good the solvent is at surrounding the ions and replacing their interactions with other ion dipole interactions with solvent. So I don't actually know in this case. They must be able to get separate enough to do the chemistry. Yeah. All right, others? Somebody out there is wondering, so do we have to know this mechanism? And my answer is no, I just spend time on things in class that are pointless. You don't believe me? Good. You're right not to believe me. You do need to know this mechanism. All right. I know it's November. Nothing is funny in November. All right. So let's talk about what if we wanted to oxidize the primary alcohol all the way to the carboxylic acid. We're going to use a related reagent. It's also going to be a chromium 6 reagent. It's not going to be PCC. And you're going to see that the reason that we can go all the way to the carboxylic acid level is because we have the presence of water and an acid. So using CrO3, I'll draw that reagent for you, but using CrO3 and H2SO4, this reaction has a name, and organic chemists love reactions with names. It's a way to indicate to your fellow organic chemists that you've been paying attention to who writes the papers. Though this was so long ago that nobody cares anymore, but we still call it the Jones oxidation after the person who invented it. You don't need to know that, but you may hear people, other organic chemists, talk about that. And importantly, the Jones oxidation can't stop at the aldehyde. And you're going to see that the presence of water here is why it can't stop at the aldehyde. So I'll show you what CrO3 looks like. And when you see the first few steps of this mechanism, you're going to say, that looks pretty similar to the PCC mechanism. I'm going to say you're exactly right. So this is also a chromium in the +6 oxidation state. What likely happens is that the acid H2SO4, which because I am lazy, I'm just going to abbreviate as HA, probably protonates one of the chromium oxygens to make it even more electrophilic. All right, so chromium used to be attached to just 3 neutral oxygens, and those oxygens, because they're electronegative, are pulling electron density away from the chromium. Now one of the oxygens has a positive formal charge on it. That's going to make the chromium even more electrophilic. So now you'll see that lone pairs on the alcohol attack the chromium, and we break one of the chromium oxygen pi bonds. It's not immediately clear why that should be the case because we don't exactly know how to deal with reactions on transition metals. The metal already has more than an octet, which is fine because it's a transition metal and has access to d orbitals. So it's not immediately clear why this pi bond has to break, and you're just going to have to trust me on that. Let's draw the intermediate that forms afterwards, though, and it will look similar to an intermediate you've seen previously, which is like this, okay? Then, likely the conjugate base of your acid removes a proton from the positively charged oxygen, and then that's going to give you the chromate ester that's identical in structure to what we saw before in the PCC reaction. Okay, so look at let's see, can we get it all on the same slide? Look at the structure of this as a leaving group and what we drew previously, and you'll see that their structures are totally the same. Okay? Like the chromate ester above, we've got a good leaving group on an oxygen with an adjacent beta proton. And so again, we're set up for elimination. And again, it's these lone pairs, this lone pair that was on the oxygen that is now in the oxygen-chromium bond. And now some base, and it could either be water or the conjugate base of sulfuric acid, some base, probably just water. That's probably the most reasonable thing to do, so I'll actually draw it, but we don't really care what it is. Removes the hydrogen, electrons kick down, and the leaving group leaves. And there you have the aldehyde. Okay? We're not done. Yes, go ahead.
If this, excuse me, if this is happening in acidic conditions,
Yep.
why are we confident that the protons are getting removed from
Why are we confident the protons are getting removed from the molecule? You know, if you left that proton on, you could still do the elimination reaction, and that would just lead to the protonated aldehyde, which is a reasonable thing to have in acidic solution anyway. So we don't, and I'm okay with that. Yep. The key step of this mechanism, of course, is not necessarily how you deal with the proton transfers, but this elimination step. Okay? Now, here's detail I'm going to provide for you that the text does not. The text says, in effect, that PCC can stop at the aldehyde because it's less reactive. That's an unsatisfying explanation when you realize that the key intermediate, the chromate ester, is identical whether you're doing the Jones oxidation or PCC, right? And if you go through an identical intermediate, then you're going to have a tough time explaining why one's more reactive than the other. I think the authors are hoping that you didn't notice. And that's okay, because the explanation requires something that you won't get in a lot of detail until 352, but we're going to do it now anyway. Yay us, okay? So to understand what happens next, remember I told you the key was the presence of water. And what you need to know about water and aldehydes is something you will learn in 352. It's called aldehyde hydrate formation. What can happen, and this, I'll try to talk you through it without, just based on things that you already understand. For an aldehyde, what's the HOMO? Oh, we were supposed to remember that. Yeah, you were supposed to remember that. HOMO is the lone pair electrons on the oxygen, right? And you're under acidic conditions, so it stands to reason that the lone pair on the aldehyde could pick up a proton from water to give you this protonated aldehyde, which I will call an oxonium ion. And the interesting thing about the oxonium ion is it has a resonance structure where the positive charge is actually on the carbonyl carbon. So when you protonate an aldehyde or any carbonyl carbon, when you protonate the oxygen of a carbonyl, it makes the carbon more electron poor. Now, if you were to look at a carbonyl compound as an electrophile, you would hopefully say that the LUMO was the carbon-oxygen pi star. And what can happen is that water will attack that pi star and the pi bond will break. You could show that step from the resonance structure I showed you below, but in the interests of keeping things simple, I won't. All right, so then water adds. You have this other oxonium ion, and another water molecule can deprotonate the water to generate this molecule, this neutral molecule, which is called the aldehyde hydrate. Now, I will point out that, and that regenerates your acid, HA. I will point out that People worry about this when I do equilibrium arrows because they're like, was I supposed to memorize or know that those were equilibrium arrows? There's never any points associated with what the arrows between reaction steps are, but this reaction is reversible. It can go backwards and forwards. You'll learn about that in 352. The important thing is anytime there is acid and water present, some percentage of aldehyde hydrate is going to form. And the relative amount of hydrate and aldehyde that you get depend on their stability, because this is an equilibrium. And so if the aldehyde is super electron poor, there tends to be more hydrate present. If the aldehyde is relatively electron rich, there tends to be less hydrate present. You'll learn all about that in 352. For our purposes, though, the important thing about the aldehyde hydrate is that you've got now OH groups, which were the nucleophiles. It was an OH nucleophile that attacked the chromium reagent in the first place. The aldehyde lacked the OH nucleophile, but now the aldehyde hydrate has it. Any questions you want to ask about how to get from the aldehyde to the hydrate? Go ahead.
Is it possible to do the same thing with the resonance structure you drew?
You bet. All that would look like you just need a single arrow. You would show water attacking the positively charged carbon.
Where did the other double bond go? Or is it?
In the resonance structure, what used to be a pi bond is now an additional lone pair on the oxygen. Yep. Yes.
Why do you care the aldehyde hydrate is now a good nucleophile?
We care about it because it can now go on to react with another molecule of CrO3. Yep. So we're still not done, but forming the hydrate first was a prerequisite to the second round of reaction. Okay. Other things about the aldehyde hydrate? Okay. And notice the aldehyde hydrate still has this proton on the carbon that's attached to the oxygen, so it can still do one more round of oxidation. All right, so let's show how that happens. We're going to do this analogously to what we did before with the first round of oxidation. We'll take protonated CrO3, lone pair electrons attack the chromium, break the pi bond. That gets you to this intermediate with the positively charged oxygen. Okay. Probably the conjugate acid of our base or water removes the proton. That gets us to the stage of having the chromate ester. I just lost an oxygen, didn't I? All right. This gets us back to the stage of having a chromate ester like we've done before. And again, recall that we're calling this a good leaving group. And this is the alpha oxygen, this is the beta carbon. We have a beta proton adjacent to the leaving group. These electrons in the oxygen chromium bond are going to leave as a base, probably water or the conjugate base of our acid, we don't care which, removes the proton, electrons kick down to form a pi bond, and leaving group leaves, and that gets you to the carboxylic acid. And again, your leaving group is this weird chromium molecule that's negatively charged. That's now chromium 4. It has been reduced and the acid has been oxidized. Okay? So That's a lot on one page, but if you think of it in stages, the first stage, alcohol to aldehyde, is basically the same thing as we did with PCC. The second stage is forming the aldehyde hydrate, okay, and that's new. But once you form the aldehyde hydrate, the third stage, getting to the carboxylic acid, is just a repeat of stage one. Okay? So, yes?
For the entire reaction from aldehyde to carboxylic acid, do you have to have two equivalents of chromium?
Yeah, so to get from the alcohol to the carboxylic acid, you're noticing that you go through 2 rounds of chromium reagents. You consume 2 moles of CrO3 for every mole of alcohol. So yes, you would need 2 equivalents. And if you were doing this, you'd make sure that you did. Now, the question that could be asked is, could I just add 1 equivalent? And would we be able to stop at the aldehyde? That's always risky. And whether or not it's going to work depends on a lot of things. In some cases, it would depend on how fast the reaction is. So for example, imagine that the reaction is a little bit slow so that as soon as some aldehyde starts to form, you still have plenty of chromium reagent around. The aldehyde that you form can go on right away to form a hydrate, and then that hydrate can compete with the alcohol starting material for the remaining chromium reagent. And in that case, you would likely get a mixture of acid, aldehyde, and alcohol, which would be a problem. So if you're going to use the Jones oxidation, you just assume you're going to have enough chromium to go all the way to the carboxylic acid.
How completely does this reaction go through if you have plenty of the chromium?
How good is it? I would say 100%. Yeah. So if you want to stop at the aldehyde, the key is, and the key difference between PCC and the Jones oxidation is right here, no water present. No hydrate, no second round of oxidation. So that's the mystery that your text didn't tell you. The reason PCC won't go on to the carboxylic acid is not necessarily because it's less reactive, but also because there's no water present to make the hydrate, and then the aldehyde never reacts with the second equivalent of the chromium. Okay. Anything else we need to do there? Yeah.
So I know you said some of this was for 352, but we also did for 85, so are you still wanting us to know this?
Yeah, I still want you to know this mechanism. You don't need to worry about, I won't really ask you about hydrate formation at this point outside the context of the Jones oxidation. But yeah, you should know how to push the arrows here. Yes?
So PCC doesn't continue without water. So would an evil trick be water? You have to know that would continue?
That's a good idea. So, but I've had it before, so it's not your fault. So nobody blame him for coming up with this idea. No, the key point is PCC won't go on to the carboxylic acid as long as there's not water present. So is an evil trick to add water to the mixture and see if it goes on further? I will say no. I promise not to do that. Okay. Do you believe me? Yeah, well. There were no crossed fingers, so yeah. Now, let's talk briefly about ketones. For ketones, either method, either PCC or the Jones oxidation, CrO3 and H2SO4 and water, either of these lead to the same ketone product. And there's no additional oxidation because there are no CH bonds now in the ketone. It is true that under acidic conditions in the Jones oxidation, you can also form ketone hydrate, I would not expect you to go on and show this as a product simply because it's the ketone is always going to be in equilibrium with the hydrate when water is present. The ketone is the desired product. But do you notice that even the ketone hydrate isn't going to do an oxidation reaction because it lacks CH bonds on the hydrate carbon. So it can't do that final elimination step that does the oxidation. So for secondary alcohols, you don't need to be careful. You can use either PCC or the Jones oxidation, doesn't matter which, either of them will work to give you the ketone. For primary alcohols, you do need to be careful. If you want the aldehyde, you use PCC. If you want the carboxylic acid, you use the Jones oxidation. All right, so thus ends chapter 12. There's a couple more things in chapter 12 that we didn't do. One is there is an additional set of reagents besides the Jones reaction, the Jones oxidation that does this same chemistry. It's not worth knowing. And then there is a section on a Nobel Prize winning reaction called the Sharpless asymmetric oxidation. And it's a reaction that uses a chiral catalyst to give you one enantiomer of an epoxide. It's interesting, and it's possible that if you take 352 from somebody other than me, they'll want you to know it. We're going to skip over it, and some of my colleagues would be, Price, what the heck are you doing? You should tell them about that. And I'm going to be, well, then you teach this class. So we're not going to cover the Sharpless asymmetric epoxidation. Yes.
You said chapter 12. Was some of this on chapter 12?
No, this is chapter 11.
Oh, okay.
Yep. Okay, so chapter 12 is a little bit different, a bit of a change of pace. Chapter 12 is on conjugation, resonance, and reactions of dienes. And that allows me to do a fun OChem joke, which is where this little character says, "Help, I'm dying." Which is probably how you're feeling at this point in the semester. So let's talk about what resonance and conjugation means. And we're going to pull back the curtain a little bit on resonance. You should be good at drawing resonance structures now. You should be good at answering the question, which of these atoms shares the negative charge or the positive charge, as an example. But you may not realize yet the molecular orbital picture that has been hiding behind in the background the whole time and really explains what's going on with resonance. So to do that, let's just briefly review what a pi bond is. As you know, a pi bond involves two sp2 hybridized carbons. And then on one carbon, you have an unhybridized p orbital. And then on the adjacent carbon, you have another unhybridized p orbital. And the combination of those two p orbitals, if we add those two p orbitals together with the same wave function sign, we get the familiar pi bonding orbital, which hovers above the plane of the sigma bonds and below the plane of the sigma bonds. And that is the pi bonding orbital. And then if we do the minus combination, the out of phase combination, what that looks like is essentially just two p orbitals on adjacent atoms, but with opposite wave function sign. And you should be used to the idea that the pi bonding orbital is filled, has electrons in it, and the pi star anti-bonding orbital is empty. And depending on the situation, might be your LUMO. Okay, that should be familiar. Everybody okay with that? Okay, that's first exam stuff. Okay. So we're going to add an element of complexity here, and we're going to consider the allyl cation. What is the allyl cation? Well, I've already told you before, the word allyl is a word that we use for the carbon that is adjacent to a pi bond. So we'll call this carbon 1, 2, and 3. Carbon 3 is the allyl carbon. And there's a positive charge on it, so this is the allyl cation. Now, one of the things you should be able to see, based on what you know about resonance, is that when you have a positive charge adjacent to a pi bond, you can move the pi bond over to form a new pi bond between carbons 2 and 3, and that leaves carbon 1 with a positive charge. Just to remind you what resonance means, and this is something that is difficult to get out of your head. It's tempting to look at those two resonance structures and believe that the pi electrons are hopping back and forth between carbons 1 and 2, and then between 2 and 3. They are not. That is false. Okay? Instead, they are delocalized simultaneously over both places. Similarly, it is tempting to believe that the positive charge is hopping back and forth. In this instant, it's on carbon 1. In this instant, it's on carbon 3. That is also false. Instead, the positive charge is delocalized onto both carbons. And this delocalization has to do with the fact that electrons are waves and can occupy more than a single point at a single time. They can spread out in space. We don't really have a great analogy for that because at the level that we live in, though all particles have wavelengths, our wavelength is so small that we only are in one place at one time, right? But electrons are very much smaller, their masses are smaller, their wavelengths are much larger relative to their mass, and so electrons can be in more than one place at once. So you've seen something before called the resonance hybrid, and I don't typically like this because it's easy to lose track of electron pairs, but it does tend to communicate what any one individual resonance structure will not. Sorry, I don't know why my voice is getting hoarse. It sounds like I'm getting emotional about this. I'm not. I mean, it is cool, but it doesn't make me cry. Okay, so we can use a dotted line between carbons 1 and 2 and between 2 and 3 to indicate that the two electrons in this pi bond are actually spread out between carbons 1, 2, and 3. And then we can use a delta, lowercase Greek letter delta with a plus, and then here, and we use the lowercase Greek letter delta to talk about really small or small increments of something. So a small increment of positive charge. About half of the positive charge is on carbon 1, about half of it is on carbon 3. Okay? You good on that? Yes?
In that circumstance, why wouldn't you put a delta positive on the second nitrogen?
Why wouldn't you put a delta positive on the second carbon?
Yeah, or second carbon, yeah.
Yeah, because if you look at the resonance structure, the delta plus is never on the second carbon. It's only carbons 1 and 3 that can be positively charged. Yep. All right. So that should be mostly review. Now we want to get the MO theory picture for what's going on here. All right. So we already know how to deal with a pi bond. As we look at this cation, And we're going to now draw this from above, try to keep it simple. If we looked at this cation, and I'm just going to draw the skeletal framework of the sigma bonds, we would expect there to be a p orbital on carbon 1, because carbon 1's involved in a pi bond. We would expect there to be a p orbital on carbon 2. What about carbon 3? What would you predict the hybridization of carbon 3 has to be? It's sp2 first because it's positively charged carbon, right? But also because it's involved in a pi bond over here in the resonance structure. If it's sp2 here, it's got to be sp2 there. So we would actually say that carbon 3 also has a p orbital on it. Okay? That's an important conclusion. So if that's confusing, we need to talk about it. Questions about that? All right. So what do we do with 3 p orbitals? It turns out that the rules of MO theory allow you to do something we haven't done so far. So far, we've always combined 2 atomic orbitals together, and we've gotten 2 molecular orbitals out, the pi and the pi star, right? Well, MO theory allows us to combine 3 atomic orbitals together and get 3 molecular orbitals out. And this can be extended to any arbitrary number of orbitals. It gets tricky though, when you only combine 2, it's really easy to figure out what they look like because you've only got 2 options, the in-phase versus the out-of-phase combination. When you combine 3 or more, it gets tricky to come up with what these orbitals look like. I'm going to show you the results. If you want to know how to come up with these orbitals, I can provide some resources for that, but it's not mandatory. In fact, what I will want you to do when we're done here is be able to look at some of these molecular orbitals that we will generate, and I'll want you to rank them in energy, fill them up with the available electrons, and decide which one is the HOMO and the LUMO. But I won't be asking you to come up with the orbital pictures yourself on your own, okay? So with that in mind, I'm maybe not going to show you in detail where these orbitals come from. I'm just going to draw them as a result, and then we can sort of move on from there. So the lowest energy combination of 3 atomic p orbitals, you take 3 atomic p orbitals together, you're going to get 3 pi molecular orbitals out. The lowest energy combination is the easy one. I just decided, no, that's fine. We'll just keep doing it this way. The lowest energy combination is the easy one, and that is where all 3 p orbitals on all 3 carbons combine with each other with the same wave function sign. So there should be a continuous lobe of electron density above the plane of the page and a continuous lobe of electron density below the plane of the page. Sometimes it's difficult to envision where this is coming from. This is what you would get. Another way of drawing this alternatively would be just to draw 3 p orbitals on adjacent atoms and show them combining together with the same wave function sign, in the same way that we've sort of done that with pi bonding orbitals before, okay? So this is the lowest energy molecular orbital. We're going to call it pi 1. We're going to drop the pi and the pi star because we got 3 orbitals instead of 2. So we need more than just no star and star to designate the orbitals from each other, okay? And notice that you expect this to be a bonding orbital because there are 0 nodes between the atoms. And notice that if there were electrons in this orbital, you would expect them to be delocalized over carbons 1, 2, and 3. So this is the orbital that represents, from our resonance structure picture, this is the orbital that represents the dotted line over all 3 carbons, or this is the orbital that represents the electrons in the pi bond that's simultaneously between carbons 1 and 2 and 3. Okay, does that make sense, or have you just given up? I can't tell. Go ahead.
Can you draw, like, I forgot what it's called, but like the 3 lines that have the electrons?
Sure. So here is the energy level where the electrons would be. And in the allyl cation, this orbital is filled. Okay, others? All right, let's show you where the next orbital comes from, this next pi 2 orbital. This is a weird one. And again, if you want to know where this comes from, we can talk about it a little bit. It won't be important for the exam. I won't ever ask you to sort of generate this on your own. But if you want to know more about it, I've got some resources. But this orbital is strange. It has a node in between the 2 atoms. It has a node that coincides with atom 2. And then it has a lobe of electron density on carbon 1, a lobe of orbital on carbon 1. And then because there's a node at carbon 2, there's a change in wave function sign as you go from 1 to 3. And then, of course, there are lobes below the plane of the page. Okay? This is the pi 2 orbital. And interestingly, there's no orbital on carbon 2. Now, you didn't know that was a possibility, but it turns out that if you do the math of MO theory, that is the result. And it's sort of required. One of the requirements of MO theory is that orbitals either have to be totally symmetric with respect to the symmetry of the molecule, or they have to be anti-symmetric with respect to the symmetry of the molecule. What does anti-symmetric mean? It just means that the orbital has to look exactly the same, only the wave function sign is different on one side versus the other side. So this pi 1 orbital is symmetric. The wave function is the same on one side as the other side. This one is anti-symmetric. It's the same except opposite wave function sign on the other side. This is the pi 2 orbital, and in the allyl cation, it is empty. Notice how that coincides with what we see up here about the place where the molecule is electron poor. It's electron poor on carbons 1 and 3, never on carbon 2. So interestingly, the MO theory picture tells us that this is the LUMO of the allyl cation. And that LUMO is on carbons 1 and 3, but never on carbon 2. That's exactly what resonance tells you. If a nucleophile were to come along, resonance would tell you, oh, I need to be able to attack carbon 1 or carbon 3. And MO theory tells you exactly the same thing. If a nucleophile attacks the LUMO, it may do so on either carbon 1 or carbon 3. Does that make sense? Okay. So the highest energy orbital of these 3 pi molecular orbitals is an easy one to draw. This is where you draw 3 p orbitals on adjacent atoms, but you have all of them be out of phase. So in this orbital, there are going to be 2 nodes, one between carbons 1 and 2, another between carbons 2 and 3, and then every time we go through a node, there will be a change in wave function sign. Okay? This is pi 3, and it is also empty in the allyl cation, but we don't care because it's not the LUMO. One thing I want you to notice is how as we go up from pi 1 to pi 2 to pi 3, we increase in the number of nodes. There's 0 nodes in pi 1, there's 1 node in pi 2, and there's 2 nodes in pi 3. Okay? So, what I want you to do between now and Monday is I want you to do this for the allyl anion. And by Monday, I want you to tell me which is the HOMO and which is the LUMO for the allyl anion. Fortunately, you don't have to draw anything new. The allyl anion has these orbitals as its MOs, so you'll just need to deal with the electrons. Okay? All right, good luck. May the force be with you, and have a good weekend.